Right, we've got a worked example here in the forces section. This is an inclined plane with a particle held in equilibrium. This is courtesy of Save My Exams. And if you have Saved My Exams, which is an excellent resource, I thoroughly recommend. You can probably see that there's a solution on there and possibly a video. I can't remember, but anyway, this is my effort. Um, let's have a look. Right. We've got a rough plane is inclined to horizontal at an angle alpha. Yes, we can see that here. And a small block B of mass 5 kilograms is held in equilibrium on the plane by a horizontal force of magnitude X. So this is X newtons here. It's a bit confusing with the N there. Coming in at this angle, it's horizontal, isn't it? So it's sort of at alpha to the plane, of course. And B is modeled as a particle, which is the usual assumption, which basically means operating from a point. You know, all the forces and the mass is operating from a point. And the magnitude of the normal reaction of the plane on B is 68.6 newtons. So it's slightly unusual to actually get that in that form. Um, all right, so probably just worth doing this little calculation here. So if the tangent of alpha is 3/4, then that's going to, if we just draw this little right angle triangle here, it's going to give us cosine of alpha is going to be 4/5, and the sine is going to be 3/5. Okay, so first things first, well, we need our forces diagram, or free body diagram, sometimes called, and so this is what we've got here. Now, I just go on about this all the time, but I thoroughly recommend that you don't scroll on the diagram here, that you create your own diagram. The reasons being that, first of all, actually creating this diagram and populating it is really part of your problem analysis. So that's a useful process to do that, even though at the time you might feel it's, time's ticking, but it's worth doing. And the other thing is, once you've drawn on this diagram, you've kind of messed it up. And if you make a mistake, or you basically, it's difficult to go back. So here we go. We've got the block here as shown, 5 kilograms mass. I'll put the units in. If it's inside a box, it's a mass. Um, Sort of two kind of um, real forces, if I can call it that way. We've got the weight acting downwards, the weight of this block, which is going to be 5G. And then we've got this force X coming in at this angle. Now, I'll put those in green because in each of those two cases, I've resolved them perpendicular and along the plane. So the weight here resolves into 5G cos alpha and 5G sine alpha coming down here. Now, on top of that, we've got this force of X newtons coming in here, and that's going to resolve into this X cos alpha that way and X sine alpha coming down there. And the other thing we mustn't forget is the friction. Now, I've shown the friction in this direction. It seemed to be implied to me that it doesn't actually say X is just enough to hold it, but it sort of looked like that. So I put it in this like this. And now the point with if you if you do actually take F in the wrong sense, it should come out in the sign of the results. We'll see if that happens. And we've also got the normal reaction. Now, the normal reaction is going to be affected by the resolved part of the weight coming down here, but also we've got this force coming down here. Okay. So, right. So in order to find the friction, and the friction, of course, the maximum friction, which is what we're actually experiencing in the limiting equilibrium case, which is kind of what we've got here. Well, it is what we've got here, is equal to mu times the reaction force. So that friction is actually equal to the reaction force, which we're told is 68.6 times the coefficient of friction. But before we can progress on this one, really we need to, we've got F is unknown and X is unknown, isn't it? So we kind of need to do something about one of those. Well, we can address X first, because if we're looking in the vertical sense, F is not, there is no friction in the vertical sense. So we've got an equation here for the reaction force, which is the reaction force is equal to the two forces in the opposite direction, because we have equilibrium in the perpendicular to the plane sense. So that's what we've got. R is equal to that, which we're told is 68.6. Right. Well, so in all this, then we know everything apart from X. So if we just substitute in all the various things, we're using 9.8 for G, acceleration due to gravity, gives us that. And if we just work that through, then that is going to give us a value of X of 49. Okay. Right. Let's just come wind down a little bit. So now we know X, then obviously that gives us this, which we can now use in our along the plane calculation. And so what we've got here is this frictional force here, I've just shown it positive in that direction, is going to be equal to the weight resolved down the plane. Well, this is acting in the same direction, isn't it? So we've got minus cos x, because AF plus x cos alpha equals 5g sine alpha, but I've written it that way. Right, again, we know all of it, don't we? We know we've got all these things. We know x now, 49. So if we put all that in, then what it works out to is minus 9.8. Right, and that kind of shows, as we are asked in part 2, the friction actually is acting down the plane, not actually as I've shown it in the diagram, since X is exerting a greater force up the plane than the resolved component of the weight is doing down the plane. Okay, so that's the magnitude, and it is actually acting down this way. Right, okay, so that doesn't quite sound like the question implies to me, but the point is, as I say, if we actually show it in the wrong direction, it will kind of work through. Um, right, so part 2. The horizontal force of magnitude x newtons is now removed and B moves down the plane. Given that the coefficient of friction is 0.5, find the acceleration of B down the plane. Right, so I've kind of reproduced the diagram here without X. Okay, now this has an effect both in the along sense and in the vertical sense. All right, so now we're looking at a net force, and we're told it's moving down. So I think now we can say that friction is actually moving up, 68.6 mu, which we've now that's probably we can take that out. So the net force is going to be 5g sine alpha minus mu r. In fact, I'll do the decent thing and just remove that. Okay, so net force is 5g sine alpha minus mu r. All right, that's friction. F equals mu r. Oh, right. And what is the reaction force? Well, the reaction force is now just as an equal value, opposite direction, obviously, to the weight resolved downwards. So therefore, the net force is going to be 5g sine alpha minus 0.5 for the coefficient of friction, times 5g cos alpha, which is the reaction force. same as that. And of course, this net force is going to equal mass times acceleration. Um, and um, and then so when we plug in the values there, equal to ma, some cancellation that goes on there that you can just check that through for yourself. That's going to give us that G equals 5a, and therefore A is G divided by 5, which is going to give us that figure. So the acceleration down the plane is 1.96 meters per second per second. All right, so I just explained all that I said before. There's a net force of 5G sine alpha down the plane, and the friction must now act up the plane. And the normal reaction is adjusted accordingly, right? So that's what that says. Okay, so there we go. So basically, that's two problems in one, really, isn't it? We've got two different scenarios, all for the price of one. But I think it nicely illustrates the fact that when we've got other forces coming in, particularly if they're coming in obliquely, as in this case here, um, then they have an effect in the vertical and also vertical in the perpendicular and the along the plane sense. So all this, in a sense, is a kind of simultaneous equations problem, isn't it? And we're putting the perpendicular against the along, and that's what helps us to resolve for multiple unknowns. Right. Okay. So anyway, that basically is it. And I hope you found that useful.